Hello and welcome to this DFT Incorporated webinar. My name is Matthew and I will be your IEEE Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today's webinar. Just to the right of the main presentation window is the Speaker Bio window with background information on today's presenter. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now I would like to introduce today's presenter, Ari Bregman. Ari Bregman is Vice President and General Manager for DFT Incorporated, located in Exton, Pennsylvania, USA. Ari has spent over 35 years in the valve industry with companies such as Nibco, Jamesbury, and Metso. Ari holds a Master's of Science degree in Mechanical Engineering from Worcester Polytechnic Institute. He is active in the Valve Manufacturers Association in the U.S., serving on the Education and Training and the Technical Committee, and is also a member of the VMA Board of Directors. Ari, welcome to today's event, and with that, I will pass things along to you to get started.
Hello and welcome everybody to DFT's webinar on pumps and compressors and why axial flow style check valves are oftentimes the best choice for protecting your high dollar and mission critical investments in the pumps and compressors in your facility. My name is Ari Bregman and I'm the Vice President and General Manager for DFT. We're a manufacturer of check valves and control valves located in Exton, Pennsylvania, which is actually in southeastern Pennsylvania, about 35 miles west of Philadelphia. Today we will talk about the differences between pumps and compressors, and then cover a little bit about how either are essential to us all and have become the absolute cornerstone energy source for so many industries. The main purpose of this webinar is to help you understand the differences among the many different design types of check valves and the advantages or disadvantages that some of those check valve styles present in certain applications. We will be talking about liquids and gases, vertical versus horizontal piping arrangements, best installation practices for valves, water hammer, and then finally get into solutions for the different application circumstances that you may have. Pumps and compressors, as I said, are the power source that make it possible to transport fluids in a piping system from one location to another with high levels of efficiency. The pharmaceutical, food and beverage, petrochemical, power generation, and specialty chemical industries rely on this equipment daily to keep fluids and gases flowing between processes in a seamless and uninterrupted manner. You'll find them in power plants, water treatment plants, natural gas transmission stations, and process plant cooling towers. Compressor or pump skids can be custom built on site, or they can be built off site and then transported by a flatbed trailer so that they can be bolted to the existing plant equipment that are used every day to keep fluids and gases flowing between processes in a seamless and uninterrupted manner. Pumps can vary widely in terms of size and output, largely depending on the liquid being pumped and the specific requirements of the application. They can range from small portable units for domestic use to large-scale industrial equipment capable of supporting whole facility systems. In some cases, there may even be several pumping stations positioned at predetermined intervals along a pipeline to maintain consistent flow rates and pressures. This is normally seen when we're transporting fluids over vast distances. Just like pumps come in all sizes, so do compressors. Everything from small to gigantic is possible. Because compressors are transporting gases, the sizes do tend to get quite a bit physically larger. Within a process plant, there can be one or more compressors. But if the gases are being transported over a vast distance, there may also be substations located every 100 miles or so to repressurize the system and keep the gases flowing. This is quite common for natural gas lines, where you may see a fenced-off area in a cornfield with a building and a bunch of pipings coming out of and going back into the ground. These compressor stations can cover distances of hundreds of miles, and the pipelines can cover distances of even thousands of miles. Regardless of whether you're using pumps or compressors, they are always a critical power source and a significant investment in your fluid flow systems. Check valves are vital protection to these pumps and compressors, ensuring safe and effective operation by allowing flow in one direction only and preventing flow in the opposite or reverse flow direction. This protection is crucial since backward flows in pumps and compressors can result in serious damage to this very expensive equipment. In this diagram, I've put a green circle around the check valves so that you can spot them a little bit more easily. What isn't so easy to see is the three dimensions of length, width, and height of this installation for these valves in this piping system. Check valves have the sole purpose of making sure that whatever is in these pipes only flows in one direction. For instance, reverse flows can cause the pump impellers to spin in the opposite direction. This can cause them to become unthreaded and disconnected from the impeller shaft. Other defects associated with reverse flow includes impeller galling, casing damage, and accelerated wear of thrust bearings as well as the mechanical seals. The damage caused by reverse flows into pumps and compressors can cost hundreds if not thousands of dollars and lead to very inconvenient downtime and reduced productivity. It's essential to ensure that you've chosen the right check valves and purchase them from a reliable manufacturer to ensure that they are durable and reliable enough to operate effectively in your specific application. In this slide, I'm trying to show what happens when flow comes backwards toward the pump with a valve in an open position. I know I've got the swing check in the right-hand side illustration showing upside down relative to the pump outlet, but bear with me on that. On the left-hand side, we see flow coming out of the pump, heading upwards, and it's pushing open the swing check valve, which is what you'd expect to have happen. But it's going to be gravity or reversing flow that's going to be closing this valve, and that can lead to a lot of problems. On the right-hand side, we're looking at that valve being stuck open for whatever reason, and it could be just wear of the pin or something else has happened, but it's not an uncommon occurrence for swing checks and double door checks to be stuck open in these vertical flow orientations, and that's just an unusable situation for these styles of valves. They just don't work well in vertical lines. This slide builds on the previous slide that you were just looking at and illustrates some of the problems associated with vertical pipelines. The flow direction, of course, compounds the issues that need to be considered. If normal flow is up, then the axial flow check valve has to have a slightly stronger spring to compensate for the weight of the disc in the stem. This stronger spring will keep the cracking pressure within the range of a nominal 1/2 psi, which is desirable for most applications, whether it's a vertical line or a horizontal line. And as you can see with the illustration of the swing check, gravity is keeping the valve open, even if there's no flow at all. If the normal flow direction was flow up, the orientation of the valve would be reversed and the flapper would be sitting on the seat all the time, as you saw on the last slide. And you might think that this would be a good thing, but it actually will lead to significant water hammer problems. The reversing flow, assisted by gravity, is going to slam the valve shut, and the shock waves from that will be significant. To avoid this from happening, the flow has to be stopped while the flow is in the forward or normal direction, and that's the advantage of an axial flow check valve. So the valve has to close before the normal flow direction reverses. Double door check valves have springs just like axial flow check valves have spring, but in the double door valves these springs are torsional springs, sort of like you'd see in the old wooden clothespins. And the types of springs that are put into those valves are purpose designed and fabricated for the normal conditions, which would be a horizontal pipeline orientation and about 1/2 psi of cracking pressure. When the pipe direction becomes vertical, the weight of the door halves will act to open the valve. Axial flow valves utilize either helical or conical spring designs, and they are very easy to make custom and to dial in small increments of closing force differences within the various spring types. And so this is the advantage of the axial flow design, the ability to customize a valve for a specific application. Although the term pumps and compressors are sometimes used interchangeably, there are distinct differences between pumps and compressors. A pump is a machine that moves a liquid could also be a slurry, from one point to another via some type of mechanical action. A pumping mechanism, either centrifugal or reciprocating, imparts energy to the fluid, thereby forcing it through the pump outlet. Pumps are typically used to transport liquids over predetermined distances at specified pressures. The overall distance and volumetric requirements of the fluid will determine the output required by the pump, which will in turn dictate the size and power requirements during the pump selection process. In sectors such as water, wastewater, petrochemical industries where millions of gallons of liquids are pumped and processed on a daily basis, the durability and reliability of pumping systems are of utmost importance. A compressor, on the other hand, is only capable of transporting gases. Compressors work by squeezing the gas into a smaller volume, causing it to store potential energy to be used when needed. Compressors are frequently used to generate compressed air, often referred to as the fourth utility. Compressors, however, cannot be used with liquids due to the incompressible nature of most liquids. In both pumps and compressors, proper and well-maintained parts and components are crucial to preventing damage, contamination, and overall system failure. There are probably more variations on what a pump is than there are check valve varieties. The types of pump, as well as the selection of that pump, mainly depend on very specific application-related requirements. The application mainly includes the type of fluid you are desiring to pump and the distance you desire to move that fluid, plus the quantity you require to get over a particular time frame. There are sources online to help you understand what type would be the most suited for your needs, and I invite you to explore the web and look for the information that's available to you there. You may at some point need to speak with a manufacturer and really get into the details of what your intended application is to get the best advice. The previous slide showed dynamic styles of pumps, but on this slide we're looking at positive displacement types of pumps. Think of the dynamic pumps as being a continuous process of pushing the liquid through the pump and into the piping system. A positive displacement style is more like a batch process, where discrete but small volumes of liquid are pushed forward by the pump. Lots and lots of these slugs moving forward creates a continuous flow, but the pressure profile for this type of pump is a bit more choppy, and small pulses of pressure exist. Move far enough away from the pump and you see less and less of that pulsing in the pressure profile, but close to it, where the check valve lives, you'll see a more pulsing nature to the pressure profile. If you've listened on any of my many other webinars, you know that I love to pull in some history into my lessons on valves and industry. These illustrations here are reminders of what was the norm for moving liquids not all that long ago. The chain wheel moves slugs of liquid in exactly the same direction in exactly the same way that a positive displacement pump works. The pump handle that you see in the middle is a very familiar outdoor fixture from probably 150 years ago, although you might still see this kind of pump being used today in many places. The last type of pump is a screw and auger type pump, and it's a continuous or dynamic style of pump. In this illustration, someone has to stand by the old style pump and turn the handle a couple of thousand times to get water up the incline and flowing into the pipe. At some point, this poor guy's arm must have gotten pretty tired, so he was replaced by either a windmill or an electric motor if electricity was available. One of the most common problems with pumps is their demanding spatial requirements. Because pumps tend to generate a fair amount of noise during their operation, they're usually put in special pump rooms. However, these rooms are not often sized with all the space requirements in mind that are needed for the valves, the fittings, and all the piping, so you wind up with a very tight fit and limited space for everything. Best piping practices dictates that there must be at least 5 and preferably 10 pipe diameters between the pump and the valve. Due to the limited space in many of these pump rooms, this recommended distance is rarely achieved in practice. Valves and other obstructions placed too close to the pump outlet can cause further disturbance and turbulence in the flow, which puts additional stress on all the elements in that piping system, whether they're valves or flow meters or whatever. Additionally, in multiple pump systems that share a common header, the sudden cessation of one pump can result in a water hammer within the piping system, and that water hammer can be very significant. Here I'm going to talk a little bit about some high cycling and extreme conditions that can be found out in the industrial world. In this slide, we're looking at a copper mine with pump discharge. It was a very aggressive service, and the dual plate valves that were installed were failing prematurely. In fact, some of the valves installed in this system were also wafer-style swing check valves. These valves were replaced by the DFT model ALC check valve. And the reason that model was chosen in this case is that the ALC has the API 594 face-to-face dimensions, so they were one-for-one change out with the existing valves, and no modifications to the piping system were required. The DFT valves eliminated the slamming issues that caused the premature failure and damage of the internal components of the valves, whether they were the dual plates or the wafer type swing checks. The system here had 6-inch through 20-inch valves. Because of the aggressive nature of the service, the valves were 316 stainless steel body and trim with Inconel X750 springs. These valves were installed on a Barron organic service, which is a kind of a reagent of kerosene to strip the copper out of the fluid. But these valves have been installed trouble-free since 2012. This slide indicates another type of high cycling extreme service condition. In this case, it's a water intake line at a paper mill. There were 3 18-inch Class 150 swing checks that were installed in this system, and there was a very serious water hammer caused by the slamming of these valves when the pumps were shut down. That water hammer caused such extreme vibration that it caused the pumps to be shaken loose from their mounts. So not only were they having problems with the damage to the swing check and the internals of those swing check valves, but they were also causing the pumps to become loosened from their mounting support systems. The solution here was to install 18-inch model GLC check valves from DFT. These were carbon steel bodies with stainless steel internals. A spool piece was added so that the overall length of the GLC would match the B1610 face-to-face dimension of the swing checks that were there. Further to that, these valves were custom sized to confirm that we had a good fit between the flow capacity of our valves and the flow requirements of the system. These valves were installed and run continuously on a week in and week out basis. The owner of this particular paper mill expects a 10-year service life. These valves have been installed since 2011 with no issues, no repairs, and just a very happy customer for these past 9 years. Whether it's flow up or flow down in a vertical line, the axial flow check valve is very often your best solution. In fact, almost always often your best solution. With pump design, a valve is often required to perform effectively while occupying as little space as possible. This is even more crucial in vertical flows where every millimeter of space is quite valuable. Axial flow check valves are ideal since they occupy less space than manual valves and other types of conventional check valves. The Axial design also offers the advantage of being able to be installed in whatever the pipe run is that you have in mind. It could be either vertical or horizontal. Low flow can oftentimes be a problem where you've got pumps that are operating at a low flow condition by design of the plant. And the outcome of that is that the check valves that are in that system may chatter, and if it's left unchecked for a long period of time, will eventually fail. When that failure happens, it's possible for the internal pieces of the pipe of the valve to break off and travel down the pipe, and then do damage to other pieces of equipment. Here we're looking at a wastewater treatment plant, 30 to 60 million gallons per day. There were 16 trains in this system. They were having severe water hammer, and they were replacing and repairing check valves every 2 to 3 months. It is a vertical flow application, and we replaced those valves with the ALC axial flow valves. There was some modification required to get the correct face-to-face dimension, because the ALC is a narrow face-to-face pattern, but the axial flow ALC valve solved the problems, and the customer is very happy with the outcome. A common problem with pumps is water hammer. Water hammer is a shock wave that is transmitted through a fluid that's contained within a piping system. The most basic explanation is that water hammer occurs when a fluid in motion is suddenly stopped or forced to stop, either by the shutdown of the pump or the sudden closing of another valve. The momentum of the fluid abruptly stopping creates a pressure wave that travels through the media within the piping system, subjecting everything in that closed system to significant increases in pressure and the forces associated with that pressure. Normally the pressure wave is dampened or dissipated in a very short amount of time, but the pressure spikes can do enormous damage in that short amount of time. Water hammer is a common issue in households, but it's also very common in industrial plants, and can manifest itself as a thumping or banging sound that in extreme cases can result in extensive and costly damage to expansion joints, pressure sensors, flow meters, pipe walls, and other valves. The spring-assisted mechanism of the axial flow check valve ensures that the valve closes well before the flow reversal, reducing the possibility of water hammering. The durable and rugged design of the axial check valve consists of no swinging parts or hinges, which is very helpful in reducing wear, but also increases the longevity of the valve itself. If you're watching the illustration going on in the background, you can see the differences between the swing check valve and the axial flow valve in the magnitude of the pressure spikes. So why are axial flow check valves inherently better than double door and swing check valves? Here we're going to look at three main types of check valves: the swing checks, the double door checks, and the axial flow check valve designs. One key factor in reducing water hammer is to stop the flow before it reverses its direction. This requires a valve to respond very quickly to the change in flow rate through the piping system. Both the double door and the axial flow check valves have springs that act to close the valve as an integral part of their designs. The springs always act in opposition to the flow, so the springs will sense a decreasing flow rate by closing the valve. However, the distance that the disc has to travel from the full open to the full closed position is also a very important part of the closure time of the valve. If the valve must respond quickly, it follows that a shorter distance can be traveled in less time than a longer distance. So let's look at the illustration and compare the traveling distance of each of these three types of valves. The swing check travels in an arc and covers a distance of 1.57 times the nominal pipe size to go from its full open position to the full closed position. The doors of a double door check valve travel a shorter distance, with each half covering an arc of about 0.785 times the nominal pipe size. The axial flow design actually travels in a straight line, And so from full open to full close, it covers a distance of only 0.25 times the nominal pipe size. Even a swing check with an external mechanism of some sort to force the valve closed before flow reverses has to travel 6 times faster to cover the shorter distance that the axial flow check valve covers. The double door has to only travel 3 times faster to go from full open to full close in the same amount of time as the axial flow valve. And the valve closure time is it's the second key to reducing water hammer. So the axial flow design really does come out ahead by both closing the valve before flow reversal as well as closing the valve faster. So now we're going to switch to talking about gases and compressibles flowing through a pipeline. You're looking at some installation pictures of our PDC valves installed on compressor systems. The picture on the left is a natural gas compressor station that I referred to a few minutes ago that could be located out in the middle of a cornfield. In this case, we see trees in the background, so it's probably not a cornfield, but it is outside. And the valves are installed outside the compressor area, and you'll see the PDC valve right where the piping changes from blue to white. And right after the PDC valve, you got a short section of white, and then there's another valve that happens to be a gear-operated manual ball valve. The piping then exits the ball valve and turns down and heads into the ground for destinations unknown. The picture on the right is a smaller reciprocating compressor application, which I believe to be compressed air. But the PDC valve installed on this piping system is very near the outlet of the compressor itself, and there is a flexible connector actually between the compressor and the piping system itself that you can see in this illustration. So here we're going to look at 3 different types of compressors. There's a rotary compressor that you'll see on the right hand side, and now we're seeing a reciprocating type compressor popping up on the left hand side, and finally we're looking at a centrifugal type of a compressor diagram. Rotary compressors contain 2 helical rotors with a housing that interlock, and the ambient air comes into the compressor through an inlet valve. Air is then trapped between the 2 rotors. These rotors turn, and what this does is it increases the pressure of the air by reducing the volume. In the reciprocating compressor, you might have a very small version of this actually in your garage that you use to pump up your tires, but much larger versions are found at compressor stations where they're used to compress natural gas as it travels through a pipeline from the oil fields to the end user locations, and quite often that's a utility, like a combined cycle power plant. It is the compression of the gases that allows the gas to continue to flow through the pipes and eventually arrive at its final destination. A centrifugal compressor is a type of dynamic compressor or turbo compressor. It's radial in design. Unlike displacement compressors that work on a constant flow, dynamic compressors work at a constant pressure, and the performance is affected by external conditions, which could even be changes in the inlet temperature of the gases coming in. So with gases especially, we're concerned about pressure pulsations. Compressors, especially the reciprocating compressors, can generate pressure pulsation within the system. This pulsation occurs due to the intermittent drops in pressure between the upstroke and the downstroke of the reciprocating motion of the compressor. These pulses of the pressure can result in a constant motion of the valve trim as well as vibration within the whole of the system itself, which can cause accelerated wear on the valves, the piping, and other components of the system. Wear of the valve's internal components can ultimately lead to gas leakage and subsequent reduction in output pressures throughout the piping system, as well as back pressure into the compressor itself, which will reduce the compressor's efficiency as well as lead to other serious maintenance problems. High cycling can wear the often used piston check valves and cause extremely high maintenance and eventual failures that then have to be addressed. DFT offers many solutions for different application situations, and what you're looking at here is a slide of our SCV or screwed end type check valve. This valve is also available with socket weld ends as well as MPT ends, but these are used quite often in small compressor applications where a tight shutoff or zero leakage is required. They can be used in horizontal or vertical orientations. They're a very durable construction. The springs are designed to last for well over 1 million cycles, and you get increased valve longevity with the SCV type of valve as compared to some of the other types of check valves that may be used in these applications. The SCVs are made in sizes up to a 3-inch nominal pipe size. As we get larger in size, we have other options available as well for either centrifugal or screw compressors or pumps for that matter. We have our Excalibur and our GLC product lines. The Excalibur is a B1610 face-to-face, so it's interchangeable with swing checks without having to change the piping system. The GLC is another option that we offer. These valves start in 2-inch line size and go up. They can be used in water, steam, gases of various sorts, compressed air. They're usable in horizontal or vertical orientations. They provide tight shutoff, and with a soft seat option can even be provided a zero leakage option for these types of applications where leakage is very critical. Finally, we get to a very specific subset of all the different types of applications that are out there, and that's reciprocating compressors. The illustration here is of our PDC check valve, which is a pulse dampening check valve. It is only to be used in air or gas type services only. It's made in line sizes from 2-inch to 26-inch, from class 150 to class 2500. As I said, the name PDC means that it's a pulse dampening type of check valve, and the design of the inner chamber does do exactly that, and you'll see that in my next slide where we have an animation of how the valve works. This valve can be used in a horizontal or vertical orientation, and is a very durable design, again with a 1 million cycle spring design integral to the valve itself. As I said, the PDC is a unique design of check valve that's made specifically for reciprocating compressors. Inside the valve is a motion dampening internal piston that acts like a shock absorber to dampen the piston's response to the pressure pulses. Because of this, the valve is a little slower to open and close, but that is really what it's desired to do for a check valve in a reciprocating compressor. Again, this valve cannot be used in liquids, only gaseous services. So that brings me to the end of my prepared materials, and now I can field a couple of questions.
Thank you so much for that great presentation. And now let's get to the Q&A. If you haven't already submitted your question, please do so by entering it in the Q&A box on your screen. Okay, our first question is, can I get a valve that will give me bubble-tight shutoff on natural gas?
Can I get a valve that will give me bubble-tight shutoff on natural gas? Well, the answer is absolutely yes. All of our valves, whatever model you select, are all available with a soft seat option. That soft seat is selected based on the media going through the valve, pressures and temperatures and so forth. But they all have a soft seat material that will give you bubble-tight shutoff.
Okay, great, thanks. Next question. How close to the outlet of my pump can I mount your check valve?
Ideally, you'd want a minimum of 5 times the nominal pipe diameter, but we see them bolted right to the outlet of the pump. The more space, the better. What you're trying to do is establish a less turbulent area for the valve to live in. So put as much space as you can between the outlet of the pump and the valve, and you will have a very happy check valve.
Okay, great, thank you. Next question. Can I mount a gate valve right after your check valve?
This kind of follows on the previous question a little bit. Can I mount a gate valve right after the check valve? Yeah, you can. That gate valve is going to live in the turbulent zone in the downstream side of the check valve, and that may also cause additional back pressure on the check valve, which could impact the pressure sizing conditions that you are running through the valve. So recheck the sizing with the presence of a gate valve and some back pressure, just to make sure that the sizing works properly.
Great, thanks for that. Okay, next question. If my outlet is a 4-inch connection, do I just bolt a 4-inch check valve to it?
Not necessarily. You might actually do the sizing and find out that a 3-inch valve is a better sizing fit. So always do the sizing on any check valve that you're installing in a system. You'll be much happier for it. An oversized valve will create low flow through the valve, which would cause chatter and instability, which is not a good thing. You'll have advanced wear if you do that. So always do the sizing, and don't just assume that the nominal line size is the size of your valve.
Okay, great, thanks. Looks like we have time for one more. How often do I need to do maintenance on your check valves?
This depends on a lot of variables. If there's a slurry going through the valve, you may have advanced erosive wear. So, it's very much based on the media going through the valve and your own experiences with other valves. So there's a lot of variables. I would recommend doing a first maintenance interval at about the 1-year time frame, just to make sure that you don't have a lot of erosion going on. But it's not unusual for these valves to sit in a line for 5, 10, even 20 years without any maintenance at all. They're very rugged and very durable. So, I would say go on your own instincts about the first maintenance interval, and then from what you see will dictate how often you need to do maintenance after that. Well, okay, thank you very much for your time and attention at this webinar. And I do appreciate your listening in, and hopefully you've learned a few things in the course of this. I also encourage you to contact your local pipe valve and fitting distributor. They can in turn be in contact with our regional salespeople to help you engineer any of the applications that you have that may be on the borderline where some special considerations need to be given. So again, thank you very much for your time and attention, and look forward to speaking with you again in my next webinar.
Great, thanks a lot, Ari, and thank you again for that great presentation. I'd also like to thank all the attendees for their participation and submitted questions. You will be receiving an email from us with a link to the on-demand version of this presentation, where you can download the PDF of today's PowerPoint after today's session. Thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.